I'm Jacob Huang, the IS Director. So welcome all of you to be our IS Distinguished Lecturer. Recently, we do have a little bit more lectures than probably you expect. So in future, we probably have a little bit less, and we promote more workshop, international conference, something. So we have a slight change. But anyway, whenever we have a IS event, we really thank you that you can register on our website before coming, because the staff can arrange the sitting sometime. Yeah, there's some case we have over 369 registration and only 100 show up. So it's really embarrassing. So we really hope all of you can register and come in time. So thank you very much. So today we have a very special and very important event, and I will invite Professor Xinyi Wang, the head of physics department, to introduce our speaker. Yeah.
Well, thank you, Professor Huang. I really like to express my sincere gratitude to Professor Huang, the Executive Director of IAS, for his support of this distinguished lecture. Today, we are really honored to have Professor Lindsay Greer from Cambridge to deliver this IAS lecture, extending the applicability of glass state of matter relating to several different forms of glass. Professor Greer is the head of a School of Physical Science at the University of Cambridge. The school is, as I found out, is actually quite large. So they comprise of 7 or 8 different units: applied mathematics, physics, chemistry, earth science, geography, Institute of Astronomy, Isaac Newton Institute of Mathematical Sciences, Pure Mathematics, and Mathematical Statistics Department. So there are like 3 different mathematics departments. And finally, but last but not the least, is material science and metallurgy. It's a very important department in this School of Physical Science. So Professor Greer is a Cambridge man. He got all his degrees from Cambridge. After that, he worked at Harvard as a postdoc and later on as an assistant professor with the late David Turnbull before he came back to Cambridge. At Harvard, he worked on metallic glass. I said a little story yesterday. I don't know how many of you know the term bulk metallic glass was first coined by in a paper published by H.W. Kui, who was actually Lance's supervisor at the Chinese U, and Professor Lindsay Greer and David Turnbull in a 1983 paper in Applied Physics Letter. Of course, that paper got thousands, lots and lots of citations. But since then, he also had a number of visiting positions at different places, notably Institute of National Polytechnic in Grenoble, Center of Study of Centre d'études nucléaires in Grenoble, and he was also the Harrison Distinguished Visiting Professor at Washington University in St. Louis. So he has received a number of awards, a teaching award, Pickerson Teaching Prize from the University of Cambridge, the Cook Abelet Award from Taylor and France, the publisher. Yeah, and the Hume Rothery Prize from and the Griffiths Medal of Institute for Materials and Minerals and Mining, and also the Honda Contaro Memorial Medal from Tohoku University, the Li Xun Lecture Award from the Chinese Academy of Science. He published a lot. He published 2 books. I brought one of them. The Nucleation in Condensed Matter. So this is 800 pages. It's got all kinds of nucleation events, including nucleation of a bubble in a beer. That's what Ken Kelton, the co-author, and Lindsay figured out in a pub, I suppose. Yeah. So it's actually quite expensive book, but if you want a discount, you should talk to Professor Lindsay Greer. So he's a true scholar. He published something like 350 papers, but his articles is really a joy to read, especially the short ones, these news and views short essays. If you haven't read it, I encourage you to read it. It's very short, it's terse, and get to the point. A lot of times he explains things, or he makes things easier to understand than the original paper. So I was really happy to read that. Without further ado, please join me to welcome Professor Lindsay Greer to deliver this distinguished lecture.
So thank you very much indeed, Shun-Li. With that introduction, it's rather hard to follow, but I'll do my best to live up to it. Our topic is extending the applicability of the Glassy state of matter. It's a great pleasure to be here in Hong Kong and City U to deliver this at the HKIAS. So, well, Phil Anderson said that the glass transition was rather a good thing to study. I think we're not going to go quite into the deep theory of it, but look at more practical aspects in this particular talk. But we are going to cover a number of examples, some of which you might not have expected, including what might happen in deserts, why frogs might be interesting, and some device applications, as well as more conventional glasses. I'm going to present this at a rather basic level in order to be appropriate for a potentially general audience, and begin by explaining that if you have a glass, I'll tell you what it is not. It is not a crystal, and so your atoms are not lined up in neat planes. But the crystal, which is so well ordered, you might think because it is ordered is particularly strong. At least in the metallic state, that's actually not true, because these planes of atoms can slide over each other rather easily, and that gives this a rather low flow stress compared to what you might in principle have. And the glass helps you to achieve that difficulty of flow, if you like. So it lacks periodicity, unlike the crystal. Its density, however, may be remarkably similar. The local configurations may be remarkably similar, but you don't have those planes, and plastic flow, at least at ambient temperature, can be rather difficult. Of course, forming glasses is really an ancient business. When I was head of Department of Materials, at least in the UK system, I don't know if it's the same here for Shun-Li, if there was any accident in the lab, it's the head of department who goes to jail. And so I was rather concerned about safety matters, so we would not have been permitting people with bare feet next to hot glass. But this is, of course, an ancient technology, an important one, gives you beautiful objects, but it also gives you very high technology objects. So glass fibers, of course, with their enormous information carrying capacity, if you get the refractive index variation just right. How to make a glass? Well, there's only one classical way to make a glass, and that's you start with a liquid. So here we've got a plot of volume of our system. It's a function of temperature. You cool the liquid, it shrinks. It might freeze to a crystal, but if it avoids freezing, it will keep going. It's then supercooled or undercooled. As its volume goes down, the viscosity of the liquid rises, and that point about changing viscosity is something we will return to again and again. As the viscosity increases, the changing structure of the liquid, and it is changing its structure, which is why this has got a steep slope, the changing structure becomes more difficult to change, and eventually it gives up and forms a given structure, preserving the configurations of the liquid in a solid state, and you have then your glass. If you were to cool the liquid more rapidly, you go through that critical glass transition sooner, and you form a different glass. Same composition, but in this case, you can see it would be a higher volume, it would be less dense. So you have a range of glassy states. And you can get such a range of states in essentially all categories of material, all types of bonding. The classes we're familiar with in drinking glasses, in windows, are oxides, silicates. Polymers form glasses, chalcogenides do, organics, even ionics do. There are many biological systems. For a long time, it was thought that metals would classically not form glasses. Then it was realized that alloys do, and it's remained an open question until possibly rather recently, I would argue, whether pure metals might form a glass, and we could also mention water. Given that vast range, it's quite interesting that again and again in the study of glasses, all of those extremely different categories are put together into one picture. Now, I mentioned the idea that the viscosity of the liquid was very important. If you're blowing some fancy piece of glasswork, some nice decorative vase or something, or a bottle, the way the viscosity changes with temperature is critical to how easy that is to do. Well, this is a plot of log scale of viscosity against inverse temperature, but the temperature is normalized with respect to the glass transition temperature, which is here. So high temperature is to the left, and that's the liquid. Low temperature is off scale to the right, and that's the glass. So we take our glass, we heat it, characteristic viscosity to go through the transition into the liquid, then we extend into the liquid state. Viscosity comes down as we heat up. Well, if you were dealing with silica, the classic glass forming system, comes down in a rather straightforward, linear way. Classic Arrhenius behavior. This is described as having a strong network, which is rather well behaved as you heat it up. But if you had something like, say, toluene, organic liquid, it comes down, it looks like it's behaving rather normally, and then it bends around. So you have this very curved behavior. It's not straight, not Arrhenius. That would be described as a fragile system. And all known glasses, or these are glass-forming liquids that will make a glass, form in this pattern and sit at various points in this spectrum from the strong side to the fragile side. And we're going to focus from our long list of glass categories on three types only: metallic glasses, carbohydrates, and chalcogenides. So let's begin with the metallic glasses. We've already emphasized that for a long time it was thought that this would be difficult or impossible. There are good reasons to think that. They're naturally crystalline for lots of good reasons, not least that their crystal structures are exceedingly simple, so it should be able to crystallize very easily from the liquid. Furthermore, a liquid metal, classically at its melting point, has a viscosity very similar to water. So the atoms are extremely mobile. But if you put some alloying elements in, the system might get a little bit confused about what sort of crystal it would want to make. And so for a simple binary system, you can adjust things so that you can get a glassy state, but you need a quite high cooling rate, up to of the order of 1,000,000 degrees per second. And classically, that was obtained by squirting hot liquid metal onto the rim of a rapidly rotating wheel, and you get a ribbon coming off. I have to apologize to the experts in the audience. They will immediately know that this is an example of a production run going dramatically wrong, because you shouldn't have all these sparks flying in every direction. But this is just a more pretty picture. But it gives you an idea that things are going pretty fast here, and the ribbon is some tens of micrometers thick only. But if you put enough elements into your mixture, the system, if you like, could get really confused. This is the sort of curve shown in textbooks, normally as a schematic, except these are real data. It says if you sit at this temperature, this is how long you have to wait before the system starts to crystallize. So you're waiting quite a while, even at the optimum crystallization temperature, and that means it's entirely feasible, following this dotted line, to cool fast enough to avoid this crystallization curve altogether. Your critical cooling rate is no longer 1,000,000 degrees per second. It might be at 1 degree per second, or indeed even less. So if you do not need to get the heat out very rapidly, you can then form in bulk. And a few centimeters, probably even higher than this now, some 8-9 centimeters diameter, is probably the current record. For this, you have to imagine that you're casting the glass as a cylinder, a bar. And that dimension of 8 or 9 centimeters is the diameter of the bar. And you could be completely glassy inside. The main difficulty here is not the glass forming ability, it's how much money you have, because that glass is based on palladium. So you will not be able to afford a bar of bigger diameter. This is a lower cost. There's obviously interest in getting bulk glass formation, but not with ultra expensive metals like palladium. This is really based on nickel, work of Johnson's group at Caltech, alloyed with niobium and chromium. This is a map of the diameter that you could make fully glassy, and it goes up to about just over 1 centimeter. The point of showing you the map is that the critical compositions at which you get the best glass forming ability are really very tightly defined. You wouldn't necessarily have thought that. It's almost like this bulk metallic glass is a compound. It's just it happens to have a compound with a non-crystalline structure, if you like. Here it is compared to an American dime. Nice sample. Now, what could we say about the structure of these systems? Well, first of all, one might argue of, if it's not a crystal, does it really have a structure at all? Well, the idea that you could think of non-crystalline things as having a respectable structure was perhaps promoted most by Burnell, famous British crystallographer, possibly equally famous in the British system for being a committed communist. And he modeled the structure of liquid metals. He called it dense random packing. And I won't comment on his politics any further, but I will say that this was a good sign of getting it both right and wrong at the same time, because it's sure that if you make a metal, and a metal is deciding what structure to get, it will be dense. That is the principal guiding principle. But if you are dense, you cannot be random. You may be non-crystalline, but you're certainly not random. So here is a computer simulated image showing copper, zirconium, aluminium atoms making a common glass forming composition. Very simple picture in 2D due to Dan Miracle. If you take coins, all the same size, you classically know what happens. Hexagonal close packing, they fit perfectly. If I were to take as the central coin a smaller one, then the ones outside would have to be lower in number, 5 instead of 6, and quite likely you'd have some gaps between them. In the metallic structure, that wouldn't be very popular. But if you were able to choose a coin in the middle of exactly the right size, then these would fit without gaps, and that would be much happier. And of course, you could do it with a larger coin and a larger number around the side. Quite amazingly, such a simple geometric picture of getting the radius ratios right and the relative populations of different sizes right as a guide to which compositions would be good glass formers is providing some useful insight. Of course, you don't need that insight in 2 dimensions, you need it in 3 dimensions, but Dan Miracle is working on exactly that problem, and this has turned out to be quite a fruitful form of work. So these are highly ordered systems. We can even quantify that thermodynamically. It's quite easy to make heat capacity measurements on these systems. So you can extract the Gibbs free energy difference, the excess of the glassy state above the crystalline state, which would form from it. So we set the crystal free energy to 0, measure the glass relative to it. First point to make is that the glass does have a higher free energy, so it is indeed metastable with respect to the crystal. It would wish to transform to the crystal. But the thermodynamicists among you will know well that the gradient of that line is the entropy. So actually the delta S, the difference in entropy between the glassy and crystalline system, is the gradient, which you'll see is 0. So these systems have a remarkably low entropy. It's the same as the crystalline state to which they would crystallize. So we should not think of these as disordered at all. Mechanical properties, we could look at all known engineering metallic materials. Here's a classic sort of so-called Ashby chart with a log scale of flow stress, and this is density. Here's your catalog of engineering materials, and the darker ellipses are the metallic glasses. And the simple, obvious point to make is that they come at the top of the chart. So these are the materials, metallic materials, with the highest known yield stresses. Yield stress being high might be a good thing to have, but any little knowledge of metallurgy would tell you it's not always a good thing to have. So if you have a classic steel, you may heat it up, quench it rapidly. It will form martensite, which will be a wonderfully hard, high flow stress material, but brittle. So it will crack rather easily. You could then warm that up, you so-called temper it. It becomes tougher, does not crack so easily, but you reduce the yield stress. So the basic take-home message is that you can either have a high yield stress or a high toughness, but you will find it difficult to do both. And here we are, the steels, showing this trade-off along this red line between at one end high toughness but lower yield strength, at the other end higher yield strength but lower toughness. You could ask, wouldn't it be nice to have both? And that would mean how far could we move this red line towards the top right of the diagram? Well, the X's are metallic glasses. The circles show you some metallic glasses with crystals inside. But the very best point is this one. And it's quite interesting that not only does that have a rather high value of this product, which you could call damage tolerance, but it's the world record value. It beats any other material. That's, in a way, rather remarkable because the classic metallurgical route to toughness, which is this thing, is to have a microstructure with boundaries within the material that can stop cracks. The glass, we would presume, does not have that. So it's amazing that you can get such a good property. So the mechanical properties might be good. Of course, you do have the fact that the glass formed on cooling a liquid, and if you warm it up, it heads back towards the liquid. This is a fun example where the glass transition temperature is below the boiling point of water, so you can take your rather hard metallic glass, dip it in a beaker of warm water, and bend it rather easily. So it's formable, as well as being, when it's cool, hard and strong. So if you thought of molding a material, molding a plastic, PMMA, your strength is A, not that high, and then as you raise the temperature, it comes down rather rapidly, permitting easy molding. If you compared that with the metallic glassy systems, you're up here, higher strengths, you can go up to higher temperatures, you get these further curves, which the black lines, quite of interest for molding precise structures, with the additional little bit of interest, not as far as I'm aware as yet exploited, that if you take them up in temperature just a little bit further, they'll go from the black line to the red line, which is crystallizing. And so actually you would get an increase in strength even at the higher temperature, which in principle might be useful. So we saw this picture earlier. This is the metallic glass equivalent from Jan Schroer's lab at Yale. So being in the US, he's using imperial units. So this is an inch. And you can probably see a picture of Jan holding the camera. It's rather obvious what this is, molded from the metallic glass. Not obvious what this is, but in fact it's a slice through this. You probably shouldn't look for these in your airport duty-free anytime soon, but the point is to get the idea across that you now have moldable capabilities for metallic systems that you would previously have associated with entirely different types of glass. More interesting, really, is probably the fact that the metal system as a glass does not have a microstructure inside like your usual metal, so you don't have grain boundaries. And because you have no internal structures of that kind, you can impose a pattern on the surface that is what you wish to impose, not what the material wishes to impose. And these showing remarkable results where you can extrude the glass into little holes in the ceramic template, down here to a diameter of these rods that would go down into these holes. The diameter is a mere 13 nanometers. Quite remarkable capability for capturing the shape of the surface, and of course easily able to give you optical patterns which you would use in various ways. This is just a little example from Japan. It's out of date. At the time when this slide was made, this was the world's smallest electric motor. So the external diameter, 1.5 millimeters. They now sell them with the external diameter of 0.9 millimeters. And inside the casing is a sun and planet gearing, so a central gear and planet gears around it. So here we are. Those gears obviously have to be rather tiny, rather well molded. This compares carbon steel and its lifetime with the zirconium-based metallic glass and its lifetime as the gear. I think this is partly to do with the better mechanical properties of the glass and the better shape of the gear wheel. It can just be so precisely molded. I skipped past something in that slide, and indeed the general properties of the glasses. In the opening selection of pictures, one of the pictures was of golf clubs. And bulk metallic glasses have been used for the faces of golf clubs because their yield stress is so high, with a rather similar Young's modulus to the crystal, not the same, but the elastic strain limit is much higher than the crystal. So you get a much better energy transfer to the golf ball. The problem really in the marketplace was the energy transfer was too good, so they're illegal for professional competitions. So metallic glasses, I've talked about general properties as though you could take a liquid and make a glass. But we saw before that depending on how fast you cool the liquid, you could make a range of glasses of the same composition. Having made the glass, you could heat it and hold it at some temperature. Its energy or volume would come down. That you could call aging or relaxation. The alternative process would be rejuvenation, raising its energy. You could access such states through different cooling rates, or you could do other things. For example, I've talked about annealing already, heating up. You could deform the glass, you could irradiate it. So let's look a little bit at these opportunities. This is a purely simulation work, and in fact, this particular paper has some problems, but I chose it for the slide because it captures the essential things I want to present, which is ultra-stable glasses, vapor deposition, and this nice diagram. So this is getting to the idea of how would you get a glassy system with a much lower energy? Well, you could, the blue dots are the things to look at. You could cool the liquid, the energy would come down, you'd go through the glass transition from the liquid into the glass. And we emphasize that if you cooled more slowly, you would be able to go a bit further before you went. But you soon lose patience with the rate of you could cool. This is work saying, well, following the red dots, if you were to deposit not from the liquid, but from the vapor onto a substrate, your substrate could be at quite a low temperature, but you would have quite a high atomic mobility because they can skate over the surface. So you've decoupled in some way the mobility and the temperature. So that enables you to go down further before eventually the system would turn around and deposit a system of higher energy. How far can you go? Well, you can get down to 80–85% of the normal TG. Quite easy to extrapolate how slowly you would have to cool to reach that if you were cooling the liquid, assuming it didn't crystallize. And the answer, incredibly, is as slowly as 10 to the minus 14 Kelvin per second. That, if you were to do it, would take you 1/10 of the age of the universe to get from the melting temperature down to TG. Or equivalently, if you were to take a standard glass and anneal it for long enough to get to that energy, it would take you again about 1/10 of the age of the universe, roughly 1.6 billion years to get there at the maximum. That's the extreme case. So these are quite interesting states. We can actually quantify this. So I showed you many times this picture of a liquid forming a glass. These are based on actual data, so it doesn't look quite the same shape as I showed already. Cooling the liquid at 20 Kelvin per minute, which is a standard sort of rate, would pull you off on this line in terms of enthalpy of the system. If you'd had that ultra-stable glass, you would be down here, and the equivalent cooling rate 10 to the minus 14 Kelvin per second. Highest rates going up to about 10 to the plus 13 or plus 14 Kelvin per second. We'll see how those can be reached later on. So the total energy difference is this range. That's quite a remarkable range in one phase because it's the heat of melting. So you can store that enormous difference in energies in one phase, something you could never do in the crystal state. Why would you be interested? Well, the ultra-relaxed states, of course, can be very resistant to crystallization, really hard. They also have a very interesting glass transition behavior, which has been studied extensively, not in the computer, but in the real systems for pharmaceuticals, for example. If you have a crystal and it melts, you can easily picture this as an ice cube melting. It melts from the surface in. If, on the other hand, you were to heat up a glass and it goes into the liquid state on heating, it's not a surface effect. It softens throughout the volume. These do not. They appear to be so dense that they're unable to undergo an internal glass transition. So the glass transition propagates in from the surface at a front. So that's certainly interesting. If you go in the opposite direction to higher energies, they become highly unstable. That sounds unattractive, but it might be attractive if you actually want to get fast crystallization, and we'll see some reasons why you might indeed want to do that. And it actually improves your mechanical properties. It moves you away from the high flow stress towards the higher toughness. So it could be an attractive thing to do. How do metallic glasses deform? Well, if at high temperatures you get rather uniform flow, this chart plots different possibilities as a function of how much shear stress you apply and what temperature you apply it at. And the one that people are most worried about is what does the deformation look like at high stresses at room temperature. And then it looks like this. Your flow localizes on shear bands, and it's rather obvious that that's a bad thing. So we'll be focusing on how you might try to avoid that. Can you constrain the system so you suppress this so-called shear banding phenomenon? And we'll also look at some other things that in this chart, if you went to low temperature and low stresses, you're in the elastic region, and you would expect nothing to happen. And we'll show that that's not true. First of all, if you do have a classic tensile sample and put it in tension, here's your shear band operation. It's not technically brittle, but it might as well be brittle in terms of the stress-strain curve, certainly catastrophic failure. If, on the other hand, you put it in compression, you don't see the glass shattering like this might. Your metallic glass is perfectly compressible, and that opens up a whole range of possibilities, because when we think for a conventional oxide glass of influencing the structure, how would you do it? Well, you could do it by, for example, cooling the liquid at different rates. You wouldn't think of mechanical processing of this glass as a way of getting different structures. But for crystalline metals, of course, that's an everyday phenomenon to use cold working or hot working to get different properties. With the metallic glass, that starts to become an option to use mechanical deformation to explore what you can do structurally, not just to change the shape, but to change the structure. And one of the things you could do is cold rolling, and then you store energy in the system. And you can work out how much energy do you store in relation to how much mechanical work you have performed on the material. This is a classic topic for crystalline metals. Behavior for the metallic glass is nice and linear. You store a few % of the work done. Interestingly, that's roughly the same figure as you would get for a crystalline metal. For the crystalline metal, this is achieved by generation of dislocations in the structure, which are defects. They have a higher energy. Should we be happy having found that number for the metallic glass? Well, probably no. We should probably be disappointed, because if you took a different glassy or amorphous material, namely a polymer, and you were to do a similar experiment, you'd store 30 to 60% of the mechanical work as a result of changing its shape. Why is the metallic glass so bad? Well, it's actually because of these shear bands, which have been studied for a very long time, back to the earliest days of metallic glass studies. So you deform this material, but the deformation is all focused in these thin planes. The stored energy there undoubtedly will saturate in some way, and then you get local heating that will relax that stored energy away also. So this is a very inefficient pattern if you're going to store energy in the system. Could you make it more efficient? Well, one way would be to take a sample, put a notch in it. We're now looking down into the notch and leaving a residual portion of material. And we're now going to compress this along the vertical axis. You get a much higher stress necessary to deform this very constrained material. That material is sitting here. You have to picture this as like a cylinder. This is the vertical axis of the cylinder, and we've sliced it in the central plane. It's a bulk metallic glass, a few millimeters across, and this color map is a map of hardness. And it's showing that far enough away from the action of the notch, you have the original hardness of the glass. But as you go into these central zones, you move along this color scale, and you actually move to regions of significantly lower hardness. In fact, it's lowered by as much as 36% at these points. That hardness change is presumably telling us something about a structural change, and the other way we can characterize that structural change is in terms of energy. So here's what the sample really looks like. Here's your notch. So we compress it, then we cut out the disk and then cut out the edge of it, put it in a calorimeter, measure the stored energy, and you find it's enormous. It's very near the energy that is presumed to exist inside a single shear band, except here it now exists throughout the material. And the energy stored in this material, which is released when you warm it up in the calorimeter, is about 40% of the heat of melting. So you've moved it to quite a different glassy state. And one way to give you a feel for how different that glassy state is here's your liquid forming a glass. If you were melt spinning at 1,000,000 degrees per second, you'd form that glass, which have a certain enthalpy. If you were forming it in bulk, you'd come down this line and you might be here. We have raised the energy of our system. We can easily plot that on this chart. And it's really quite straightforward to work out if you wanted to make this high energy glass by cooling the liquid, how fast would you have to cool the liquid? And the answer is about 10 to the 10 degrees per second. Of course, if you were really cooling at 10 to the 10 degrees per second, you certainly couldn't have it 2 millimeters across because you could never get the heat out rapidly enough. So the point is that we have actually made a glass with a structure characteristic of this cooling rate, where the glass was actually made at a cooling rate some 7 or 8 orders of magnitude lower, but has been raised in energy later by the plastic deformation. Interestingly, it's not very much plastic deformation. The strain is exceedingly low. Here's the stored energy in this chart, measured relative to the melting temperature. And there are a couple of little bars next to it, one labeled thermal cycling and one labeled elastostatic loading. And we'll just look at those processes. You'll see that these processes raise the energy of the system, not as much as I've just been talking about, but they do raise it, and they're exceedingly gentle processes, to the extent that you probably wouldn't have expected anything to happen here at all. But they do throw up some interesting points. So let's look at the first of those, which is to say, when you have a glass inheriting, in some sense, the structure of the liquid, you could, and I've mentioned this briefly already, imagine that that's the perfect material that has no microstructure. It has no grain boundaries, it has no second phases, nothing. So is it completely uniform? Well, it seems it's not. If you actually take the surface of a metallic glass, map out local stiffness across the surface, you could do that for the glass, for the material you get by crystallizing the glass, and by a classic strontium titanate crystalline substrate. So the local variation in effectively modulus here is about 0.08% from side to side from the center on that strontium titanate. If you do it on the crystallized material, it's the same sort of range. Look at the glass, it's up to 4 to 6% plus and minus from the central point. Quite a vast range, and odd that that should be true. It's presumably, it seems undeniable that it is heterogeneous. It presumably inherits that heterogeneity from the liquid. Given that it is heterogeneous, it's then not so surprising, perhaps, that if you look at the structure of a glass, here, of course, you've got diffraction data at different temperatures, and you go to lower and lower temperatures, you're getting what should be simple thermal contraction. And if it were thermal contraction in a simple way, it would be like you would just take a photograph of the structure, and as you go down in temperature, you have the photograph at somewhat lower magnification. So everything would scale perfectly. You'd have affine displacements. But when you look at the differences between these curves, and you compare it with what you would predict if it was affine, it doesn't work. Classically, we'd say in the picture where you're cooling a liquid to form a glass, the liquid structure changes with temperature and the glass structure does not. But that seems to be too simple. The glass structure is also trying to change with temperature, and in fact it damages itself as you change the temperature, and in that way you accumulate excess energy. The second very gentle process that I mentioned was this business of what was termed elastostatic loading. The experiment could not be simpler. You take a rod of some metallic glass, a cylinder with flat ends, you load it in compression under the yield stress. It could be 80%, or as low as, or here 95%, but in any case it's in the elastic range. You leave it for quite a long time at room temperature. You get a tiny amount of creep, And you then take the load off, look at your metallic glass, and you'll find its properties have changed. For example, can show much better plasticity after undergoing this process. We can also measure the internal energy of the system. Here's the calorimeter trace for an as-cast glass. This area is the energy stored in the original BMG. You can increase it with this elastostatic loading at room temperature. You can increase it even further if you do that loading at liquid nitrogen temperature. And the energies are quite substantial. And we can map out what those energies are stored as a result of all these different compositions being processed at different stresses and different times. In the business of storing energy in these systems as a result of deformation, I have talked in terms of percentages. So I have said, for example, in classic crystalline metal rolling, a few percent of your work done is stored as energy in the change structure material. And in the metallic glasses, we were getting rather higher stored energies, but it's some percentage of the work done. This turns out to be exceedingly odd, because we can work out the work done and compare it with the stored energy. And the stored energy now is not a fraction of the work done, it is several times the work done. So in fact, you can get stored energy that's almost 20 times the mechanical work done on the system, which must say that the energy comes from something entirely different. The work done, of course, is exceedingly easy to calculate from the distance moved by the load. So it can only be that the loading is inducing an endothermic disordering that's drawing in heat from the ambient surrounding the sample. So again, an interesting process that needs further study. We go to end our talk with a couple of mentions of these other systems. And I'll mention carbohydrate glasses and one of the principal dangers to life, which is dehydration. So if you were this plant in the desert, you would get very dry. The point is you want to come back to life when the water comes along. And I'm hoping my video might work. Let's see. Yes. So this is a resurrection plant swelling as it hydrates. And the movie's about to run backwards, and it will shrink. Now, of course, the idea that something would swell and shrink as you put water in and take water out, that's easy. What's not easy is making sure that this is alive and well after that. Because the cell, of course, is a little bag of water. You have a membrane around it. The water has things dissolved in it, salts and sugars. If you dehydrate the cell, the most likely thing is that the solutions inside become supersaturated. You'll precipitate out some crystals. The cell continues to shrink. The membrane tears itself apart over the crystals, and the cell is dead. So how do you solve that problem? Well, you solve it by forming a glass. So here's the classic phase diagram. Eutectic help you to get a glass forming, but this is not a metal phase diagram. It's water and sugar. Could be any sugar. This happens to be sucrose, but it doesn't really matter. If you cool that down and you get ice, this would be bad news for your cell, or if you've got salt or sugar crystals equally. But if you cool down and you do it just here, you would cool across this line, avoiding crystallization, across this line into the glassy state. Then you've taken a bit of water out of the system, but you've now got a congealed glassy state inside where all the biological structures inside the cell, the nucleus, etc., are preserved, so it will rehydrate quite happily. Of course, the real system doesn't do it by temperature change. It does it in a way that you don't normally ever think of in a metallurgical phase diagram, which is moving sideways, because it's quite straightforward to dehydrate this. So you're moving to a lower water, higher sugar content, but again, crossing the glass transition boundary. This is the technique that seeds use to preserve latent life despite being thoroughly dry. And it's not restricted to plants. Animals do the same. This is admittedly a rather primitive animal. They'll be found in little pools around, let's say, the Great Salt Lake. Water recedes, the sun shines, the pool dries out, the worm dries out as well. And if you are unkind enough to hit it with a hammer, it will break into many little pieces because it is in fact a sugar glass. But if you didn't do that and you poured water on it, it will come back to life quite happily. Interestingly, we sort of do the same. If you start to dehydrate humans, our systems vigorously start pumping up the sugar level in our cells, which is exactly what we need to do to vitrify, to make a glass. It's just that we're not ultimately very good at it, and we wouldn't be very happy shrinking like the resurrection plant, because of course our bones don't shrink. But possibly if we were deboned, we could be dehydrated and rehydrated more successfully. And this is the cleverest frog in the world. Admittedly, it made a rather bad life choice of living in Canada north of the Arctic Circle. So if you're cold-blooded like a frog, that means in the winter you freeze. There are living systems, Antarctic fish, that live all of their lives below the freezing point of their own blood, and there are mechanisms for doing that, but it's a very tiny temperature variation, 1 or 2 degrees. This is going to go much lower in temperature, so this cannot avoid ice formation. And normally, if you have ice formation in a living system, it will be dead. And the reason it's dead is, again, pictured in terms of the cell. So you've got your membrane, you've got liquid inside, liquid outside, and you have a balance of the salt concentration, so you have osmotic balance between the two. Imagine you grow ice in the cell. The H2O there is what is in the ice with essentially nothing else. So ice is pretty much pure H2O, unlike the liquid outside. So as the ice grows, this liquid becomes more concentrated in salts. It upsets the osmotic balance, so it draws more water into the cell, which simply allows the ice to grow even more. So you set up a pump, the cell will get bigger and bigger, will burst, and it's dead. You might think it will burst. Many people think that the problem with freezing cells and bursting is to do with the expansion on going from water to ice. That's too small to be problematic for the cell membrane. That's not the issue. It's this osmotic transfer. The frog has figured out a simple and effective way to get around this problem, which is to make sure it has something outside the cell that's extremely good at nucleating ice. So now the ice forms first outside the cell, and all the processes I told you about together already work in reverse. So now it's the salts getting concentrated in the liquid outside. The osmosis goes in the opposite direction. The cell dries out, but as you know from the desert plant, drying out is not a problem. If you've got the composition right in here, it will simply form a glass. So in the winter, the frog is completely solid. Very roughly, half of it is ice in the intracellular spaces, and the other half is a sugar-based glass. And in the spring, it thaws out and hops back to life. It would not work if you put it in liquid nitrogen. It has to be cooled slowly, because it has to have time for the osmosis to take effect in the cells. So don't put any frogs in liquid nitrogen. This idea of controlling freezing in natural systems to avoid it by glass formation or promoting it as bacteria do to actually deliberately induce frost damage, which benefits the bacteria but not the plants, is pretty widespread in nature and is of extreme interest in the medical domain for preserving things, where people are very interested in, of course, cooling and either deliberately avoiding freezing or promoting freezing. And how does the frog nucleate the ice? Well, it has a very highly developed protein which has the hexagonal pattern on the surface to match the ice pattern. What's remarkable about the protein is that most proteins will want to be compact and folded. This is deliberately unfolded in order to get as large an area as possible, which is what you need to have the most effective nucleation of the ice. And that's to put the ice in a safe place, not a dangerous place. My last topic, which I'll zip through quickly, is the chalcogenides for storing data. We're now looking at alloys based on tellurium, selenium. We're again looking at glass and crystal. This case, the glassy state is a bit more semiconducting, crystalline a bit more metallic, so switching between the two is of interest. And it was first of interest in optical discs, where you have a thin film of chalcogenide, and you do the switching by hitting with a laser. So this squirrely pattern of black and white is the grain structure of the thin film, crystalline. That's what you have in your natural disc. These tracks are the grooves, and the lasers write data in the form of these sort of fishtail-shaped things, which lack the internal black and white pattern of the grains, because that is glassy, cooled at a rather high rate, possibly of the order of 10 to the 9 degrees per second in this system. And it cools into the glassy state, and that's how you write your data. More or less a ternary diagram of compositions: tellurium, germanium, antimony, different families of compositions for different DVD, RAM applications. The modern interest, of course, continues to some extent in this, but the real interest is in doing something different. And it's in taking a thin film, putting a current through a little heater, and using an electrical current to switch the material rather than the laser heating. And when you do the writing and erasing, it's of interest to think which way round you do it. The writing is making these amorphous marks. You do that by heating the crystal up, melting it. It's a tiny volume, quite hot, surrounded by a lot of what's relative to it, cold material, so it's cooled very fast. And then you erase by just warming this up a little bit, and it crystallizes. How does it crystallize? It can crystallize internally or from the edges only, two different modes associated with two different classic families of material. This is how it would look electrically. A sharp, high-temperature pulse induced by passing a current through melts the material, quenches into the glass. The glass, warmed up, heated more gently, will crystallize, and that takes you to and fro. The rate of crystallization is critical. It must be fast to have fast switching, but you want it to be slow once you've got your data stored. You don't want this to crystallize on you when it's sitting on your shelf. So it must be both fast and slow, and that is made possible by exploiting the temperature dependence. And you can speed it up a bit by seeding it with little crystals, and they're now down to about 500 picoseconds switching time in optimized systems. So the key thing for speed here is to understand the crystallization. Various device implementations over the years. This is one from Intel and Micron. They're making the points about it being non-volatile, 1,000 times faster than other systems, 10 times denser memory capacity than conventional stuff, and so on and so on. So this continues to advance as a technology. I've said you melt, form the glass, crystallize the glass, you switch to and fro. How often can you switch it? Well, it carries on up to about 10 to the 13 reversals, so that's good enough. You don't have to go all the way between the resistance of the glass and the resistance of the crystal. They're nearly 2 orders of magnitude different. You could step to intermediate states in a given volume. That has excited a lot of interest because, of course, it's a little bit like our brains, where you get multiple signals coming in before you achieve the switching. So you have a sort of natural additive function in there. So people think of mimicking brain architectures in these chalcogenides. I think this is as yet rather exotic, but it's certainly much found in the literature. But the more ordinary memory is certainly in use already. But you can see that even from a memory point of view, if you didn't have to just do zeros and ones, but you had all these intermediate steps, and if you could really address the intermediate steps reliably, rather than hitting step 7 when you really meant to hit step 8, then that would be a complete transformation of how you do memory. And you'd step, here's the additive function. Number of pulses are driving it, and then it will switch at some critical values. So you've essentially managed to make things add up, implemented as a memory device. We wanted to study the crystallization. It required fast heating to in some way mimic the device. A conventional calorimeter simply would not do that for you. Nowadays, you can get your entire calorimeter on a chip. So everything is tiny, including your sample. And therefore, you can get access to very high heating rates, some 40,000 degrees per second. And homemade systems can go to 1,000,000 degrees per second. This is a commercial instrument. Those familiar with crystallizing glasses, particularly metallic glasses, will be familiar with DSC traces, where you get a crystallization peak. And they'll also be familiar with the idea that as you go to higher heating rates, the peak shifts to higher temperatures, and that gives you an activation energy. And that plot looks rather like this. These would be conventional data. What we found is, as you go to higher heating rates, this doesn't continue as a straight line, but bends over. So you get this curvature. So the conventional picture is you get a straight line, the gradient of which gives you an activation energy. This gives you this curvature. What's going on? Well, we realized that what's going on is simply this pattern that we saw before, that you heat the glass up, it crystallizes. If you're just at very tiny heating rates, you're at very tiny upward extensions of temperature, sure, you're in a linear regime. But if you go further, it will bend round. Metallic glasses sit in the middle of this range. The chalcogenides we found are much more like toluene. They have a very fragile behavior. So you can actually get the shape of these curves, not by measuring the viscosity, but by measuring the rate of crystallization. These are the same data plotted on a log scale and linear scale. The only point I really wanted to make is let's look at the temperature scale. This is the melting temperature. Conventional calorimetry limits you to studies in this range. Going ultra fast enormously extends the range you can reach up to near the maximum in the crystal rate, and that made it useful for understanding device performance. It's now fashionable, because of that paper, for the electrical engineers to have given up on the idea that everything is Arrhenius, and they're now prepared to admit that things can be non-Arrhenius in their kinetics, which is really just seeing this range of temperature performance in real devices. There are some systems where, of course, you get bits of curvature, but long bits that are straight. And this was completely unexpected from our calorimetry. And then we were even more surprised to find that it was confirmed by laser measurements, completely different technology. So there's something funny going on here, where you're getting Arrhenius behavior of crystallization, this long straight line, in a region where you don't expect it. And we think what's going on is this, that it's increasingly become clear that some systems are neither fragile nor strong, but both. And they're fragile at high temperatures, strong at low temperatures, first identified or proposed for water itself, and then for some metallic systems, because that gives you a long bit of what is, to my mind, entirely accidental Arrhenius behavior in the middle. Not, if you like, a true Arrhenius behavior at all. This is our chalcogenide showing this Arrhenius portion. And the really neat thing here is that the high temperature fragile liquid is essentially metallic, and the low temperature strong liquid is semiconducting. So you get an electronic transition as well as the structural one, which of course is of extreme interest for device performance. This just shows the range of crystal growth rates and is my very final topic. Here's our chalcogenides, high crystal growth rate at a particular temperature range. And because the crystal growth rate is high, the switching is fast. And because the switching is fast, this is a viable memory technology. But where does this sit? It sits between a classic metallic glass and a simulated pure metal. And there's many orders of magnitude in crystal growth rate there. And it's quite embarrassing for metallurgists that something so simple as crystallizing a metal is essentially a gap in existing theory. This is extremely badly understood, if at all. So there's work for us to do. But it also raises the question of, if we wanted to get even faster switching, well, we certainly shouldn't go in the metallic glass direction. They're, in fact, the glassy state is too good. It's too difficult to crystallize. What you should do is head in the pure metal direction, which brings us to the question of, can you get a pure metal glass? Well, it seems you can. This was Scott Mao's work from Pittsburgh. BCC pure metals, quenched at this calculated rather high rate, as you can see, in what is conceptually rather a simple experiment, which is bring together two nanotips in the electron microscope, put a current pulse through, you melt a little liquid bridge, which cools rather rapidly. What's neat is, if this is, let's say, liquid tantalum, it's in contact with crystalline tantalum on either side. It then freezes into a glass, but you cannot claim that that glass formed because it had difficulty nucleating crystalline tantalum, because it was already in contact with crystalline tantalum. So it could only form if you suppress the growth of the tantalum. And it's interesting that you appear to be able to do that even in a pure system. And then he had a nice play with it. Here's his amorphous bridge in the microscope, and you can map out these boundaries between the crystal and glass. He put another tiny electrical pulse through and was able to show that this interface moves forward a little bit. So he could play with that interface, which is just the sort of thing you'd want to do for a memory technology. And in case you think the last brick in the arch might be missing, well, actually, no, it's not, because this has now been implemented with antimony. So this is a proper memory structure based on a pure element, not a chalcogenide alloy. This is by no means a practical device. It works for switching, but only below room temperature. So you'd need to keep your computer somewhere very cold in order to get it to work. But it's a start. And the point is that if you can do it with a pure element, you don't have to worry generating really tiny volumes, which of course is what you want to do for higher memory density. The problem with having a really tiny volume on an alloy is how do you make sure the alloy composition is the same in every tiny volume? You don't have to worry about that if it's a pure system, or at least if you ignore impurity questions. So that's my point to end on, that really I hope I've convinced you that the liquid is in some way interesting because it can give you so many different glasses, and that we now understand there are some issues to do with the complexity, that these systems are not as uniform as we might have thought, and there are interesting compositional effects. So we can say that we've looked a little bit at metallic glasses, carbohydrates, and chalcogenides, and whether you're looking at viscosity as a function of temperature or growth rate as a function of temperature. Here is silica on this side. This would be like a pure metal system. This is like a pure metal system. You get spectra of behavior which relate the different glasses to each other, which is quite remarkable. You don't tend to get similar correlations pointed out for crystalline materials. And that's our point where we'll leave it. Thank you very much.
Well, thank you very much, Professor Greer. The three different glasses, very different usage, especially preserving life. So
Yeah.
we all need to figure out how to extend our lives. So are there any questions for Professor Greer?
Someone is beginning to talk, I think it's the rate of cooling required, depending sensitively on alloy composition. Is there a geometrical understanding of why that is?
The best understanding to get you furthest towards an answer is not geometrical, but chemical. And it is, if you picture a eutectic system, it's at the eutectic point that you have the lowest existence of the liquid thermodynamically. Above that temperature, it cannot crystallize because the liquid is a stable state. Below the glass transition temperature, it cannot crystallize because you've frozen in the structure. So it's the gap between the glass transition temperature and the liquidus temperature that's the dangerous zone for crystallization, and that's the one you must get through fastest if you can. So that chemical picture takes you quite a long way. But it turned out that this idea of having stable clusters, which was essentially a geometric argument with no chemistry, took people a surprisingly long way to identify stable structures in higher component systems. We're very far from a fully resolved answer here. And the real world of glass formation has yet other factors that are just plain messy, like what impurities do you have there? And in these very best glass forming systems, one characterizes how well you can make the glass by how big the sample could be. But that's a very bad measure. For the good glass forming systems, it's not the intrinsic composition that's limiting at all. It's how clean it is in terms of what particles have you accidentally entrained that would nucleate something.
I can start a question. So this last example, chalcogenide,
Yeah.
very useful, has lots of applications, but the switching time of crystallization extremely fast.
Yeah.
On the order of 10 to minus 9
Yep.
seconds, picoseconds. So the kind of cases that we're familiar with, metallic glass,
Yeah.
slow process, where it involves diffusion, so atoms have to move around. You bring atoms over here in order to form the desired phase before you can crystallize. when the time scale is reduced to this tiny, 10 to minus 9, what are the mechanisms that were driving this level of crystallization? Or maybe what is the role of the diffusion, or how does the crystallization kinetics look like? Has anybody done a study of the kinetics, how structure evolve?
So first thing to say is these must be systems, if you want fast crystallization, where the crystal has the same chemical composition as the liquid or the glass.
Exact.
Exact. And even if it weren't exact, it becomes exact when it grows that fast because it has not the capability of transporting to get different compositions. So it's polymorphic crystallization. That's the first bit of the answer. The second bit is probably where I would find myself unpopular with the main chalcogenide community because they were fascinated by the idea that the crystallization is so fast. And therefore, we're trying to say there's something really special about these systems to enable it to be so fast. My idea is actually they're not particularly special. They sit in a spectrum from slow to fast, but they don't look unusual in that spectrum. So I don't think they show anything very special, but it brings me to the final point, which is what is the mechanism? And it's something like what this is in the gap where I said theory was essentially missing. So it's, however, most closely addressed by David Turnbull's model for what he called collision-limited growth. This is different from diffusion-limited growth. So the diffusion-limited model is very primitive. You've got your crystal-liquid interface. You sort of picture atoms hopping from one to the other, hopping at a diffusional hopping rate. In a good high-temperature liquid, you can calculate what those rates are. And if you assume that every single atom jumps in the same direction, that will give you a maximum possible rate of crystal growth. That will be 10 meters per second. But we can measure crystal growth rates that are 100 meters per second. So that model must be wrong. And what Turnbull showed rather nicely, of course, it's not really the atoms that move, it's the interface that moves. An individual atom doesn't have any need to make a diffusion jump. It just has to shuffle a little bit to fit into place, to fit the crystal rather than the liquid. And his idea was that the limiting velocity for that would be much more like the speed of sound. So you'd then be a few thousand meters per second as your limiting velocity. Well, we're pretty sure that's wrong as well. And so actually the real answer for the limiting velocity is between those two, between 10 and 5,000 meters per second. There's no good model at this point for saying
That's
what
a good problem for the students.
How about the martensitic transformation? Is it
Yes.
similar to this, what you just described?
Well, some people think of it as like a martensitic crystallization, but of course I have trouble with that if one side is not crystalline.
Okay, I have maybe a stupid question, but how the oxidation rate for the bulk metallic glass compared to a similar composition of alloy? Is that would be different, or is it similar?
This is the rate of
Oxidation.
oxidation. Yeah, well, that's interesting. We could talk oxidation, which you might think of as dry corrosion or wet corrosion. The glasses are uniform in chemistry, so you don't get your electrochemical couples so easily. So there are lots of reasons why you could expect superior resistance to corrosion of any kind. And that's further made the case that you can put alloying elements in to higher levels than you would in a crystalline system, like, say, chromium and phosphorus into an iron-based system, so they become exceedingly corrosion resistant. But they don't have to be. You can have compositions that will corrode very readily or oxidize very readily. So they can be superb, but if you try hard enough, you can make them really bad at oxidation resistance as well. So a classical copper zirconium glass, the zirconium will oxidize very readily and leave you with little copper stuffs on the surface. So it's complete spectrum.
Yeah, look like Young has a burning question.
Professor Greer, okay, so, I think I have a question. So when we talk about the glass and the liquids, I think one fundamental question is, what is glass transition, right? So you talk about the crystallization, right? But how useful this phenomenon could be to make devices. But the question is, what is glass transition? Because it's related to the origin of heterogeneity. And so now, if we go out of the metallic glass field, if you go to the condensed matter field, so they have many theories, like Adam Gibbs theories and then random first order train theories. That theories will explain what is the length scale and heterogeneity would be, right? So what's I'm just wondering, in the field of metallic glasses, it seems like people are not very enthusiastic about those theories. So what's your view towards the theories? Do you think that could be useful for us to understand the problem we're facing in the field of metallic glasses?
Well, I didn't say very much about that in the talk, and that was for a good reason, because I didn't feel I had anything very valuable to say on it. To me, one of the more interesting aspects of it would be, if you're making a heterogeneous system, what's the characteristic length scale?
Right.
And I'll just comment that from if you like, an experimental point of view, I think that's looking to be some tens of nanometers. But how we come with that number and how different that would be for different fragilities of liquid, which is one parameter that people think about, strong versus fragile, and different cooling rates,
Okay.
I think there's much to study.
Yeah, if we follow the question, I recall that in 2009, Professor Wang published papers on fractal packing of atoms. Because if fractal, the length scale have many length scale.
Indeed.
We don't have length. So how can we just fit that picture into this fractal packing picture? Do you think that it's possible that our length scale will have just like time scales? Could we have a variable length scale in these amorphous structures, but you can only see it when the time's right?
I mean, in some sense, that must be true, that you have a great range of length scales operating at the same time. And to turn that around, we know for sure you can have great ranges of time scale operating. Right. So, as you will know from the relaxation kinetics of the metallic glasses, the time over which things happen, they show some 7 or 8 orders of magnitude range in the characteristic time constants in one curve. So you must have similar things for the length scales.
Right.
Yeah, which of course maybe feels we don't really know where to start in understanding it.
Oh, thank you. Actually, it's similar to what Professor Wang asked about the fast rate. We did some colloids experiment, and we studied the relaxation of glass in colloidal glass. Usually, we found it's the eigenmodes, or the vibrational modes, or it's similar to phonons in the crystal, which controls the relaxation from one state to another. You said, actually, I also agree very well about what you said. It's probably the rearrangement of the atoms which make it from one phase to another. So in that case, the eigenmodes or some the modes in the glass that can make rearrangement and the change in configuration. Do you think in that very rapid phase transition, do you think whether it's possible for this eigenmode to drive the phase transition like what we found in some colloidal glass, the relaxation?
I really don't have a clear view on that. I maybe have, this is what I should never do, is turn the question back to you. But people quite often think now of using colloids as model systems to understand what the metals are doing. But I have a worry about that, because certainly in some of the colloidal systems, they will crystallize because the crystal has a higher entropy, not a lower entropy. And so I wonder, can those systems ever be a good model for the metal? But returning to your question, I think I'm really saying I don't have the answer. Yeah.
Okay. All right. So we'll give it to Lindsay.
Very nice talk, Professor Greer. I have two small questions. The first one is we know that crystals have a long-range periodic, and glasses like metallic glasses, they have short-range and medium-range order.
Yeah.
So what is the specific length scale of the ordering structure for distinguishing the glass and the crystal? This is the first question. And another one is glass transition a thermodynamic process or a purely dynamic process?
Well, I'll start with the second one. I mean, classically, one would say that glass transition is dynamic and not thermodynamic. Is there an underlying thermodynamic transition? I can understand why people would like to find such a thing. I don't think so. I think we're living in the world of kinetics.
It's highly controversial. I mean, whether or not it's
I wouldn't, but I'm not too worried about even, say, the Kauzmann paradox. I mean, I'm pretty sure you can get real systems where the liquid amorphous state has a lower entropy than the crystal. So actually you invert and you get an inverse melting phenomenon. So remind me of your first point was length scale for glass and crystal, telling the difference. Ultimately, something around the unit cell scale, I guess. We now understand that you can get extremely, extremely fine-grained polycrystals. Yeah.
Sure.
So I think, and that's made of